Thank you for inviting me. My name is Albert Cohen. I'm a research scientist at Google, based in Paris. I've been working at Google for about 4 years, looking into building systems that accelerate machine learning from like devices like phones all the way to like cloud services, and also using machine learning to build such systems. For example, maybe you know about compilers. These are the tools that transcribe like programming languages for human beings down to something that runs fast on the machine. There are lots of heuristics, lots of optimization problems there, and we can use machine learning to solve some of these difficult optimization problems. Right. So this is all my expertise is in compilers. Which is a specific subfield of programming language, research and engineering. So I've been working on compilers for now 25 years, kind of, on mostly compilers interested in performance first, like optimizations, and more specifically parallelization. That's the field where we are taking a programming language that's essentially, since it's for humans first, it's based on sequential reasoning or mathematical formulas, depending on whether you are into math style of thinking or more, let's say, operational ways of thinking, and translates it into an execution on a machine that's widely distributed, that's capable of running many things in parallel, which is not something that the human mind is typically naturally capable of. And the process of automating this translation from a sequential execution, or at least mathematical equations, to something that's parallel, that runs fast on a distributed machine, is my field of expertise. It happened that machine learning recently is all about that as well. So it's math equations, like neural networks are just gradients and like differential calculus applied to optimization problems and classification problems in artificial intelligence. And most of the work happening underneath to make these equations run fast is hidden in what we call machine learning compilers. So translations that will automate the process of extracting parallel computations, independent pieces of work, and orchestrating resources of the parallel machine to execute these problems, these math equations, very fast. This task is of course a well-known old problem, but one of the difficult challenges has been not only to optimize for like local tricks to make the program run faster, but mostly to get the program to run distributed, to run in parallel on many devices. So if you have like a modern architecture with multiple cores, multiple processors, or accelerators like GPUs, maybe you heard about that term, they are capable of running many computations in parallel, thousands of computations in parallel. And this is not how the human brain typically thinks when we are programming. So you need a translator, you need a compiler that will automatically figure out what can be executed in parallel, how to orchestrate the resources to do this efficiently, and how to make it completely transparent for the machine learning engineers, for example, who don't want to think about the exact machine they are running the code on, but how to still translate their way of expressing the programs, the algorithms, into fast parallel code. I'm also using machine learning as a tool to build these compilers, these systems, mostly to try to optimize, to build optimizations automatically, to try to build better algorithms for translating human understandable programs into machine programs. And that involves a lot of optimization problems that are difficult, and machine learning can be a tool in doing that. So that's a great question. So I've been actually an academic. I've been working at INRIA, which is a French research institute for computer science and applied mathematics, for many years. And then I decided to switch to industry after having many actually more like fine-grained interactions with engineers in industry building real systems that I've been using in my research, and that contribute to the platforms that are being used in the world, mostly through open source platforms, like free software that's being used for compilers, free software that's used in the operating systems, for example. And through these like fine-grained, tight interactions with engineers, I really had the impression that at some point I could make a difference by not only doing research with students who eventually graduate and go to industry, because there is a high demand for this type of skills, but also carrying that research myself in a lab, in an industry lab. And there was kind of, let's say, nice conjunction of things that happened around the years 2016 to 2018, which is that machine learning was of course becoming very hot, and in clear need for the type of competencies I had around these parallelization techniques. So being able to automate the work of compilers for machine learning to run fast on the accelerated hardware. And at that point, it was like a unique opportunity to actually bring this research closer to production, closer to research labs in industry. And I was very privileged to be offered that chance, also bringing some colleagues along with me to do that. So this is very hard to generalize. Of course, it highly depends on the industry and on the domain. So right now, Google Research is clearly one of the dream places you would like to be to do research in industry, because first of all, there is a lot of understanding of what it means to do long-term research. Of course, this is applied research, but we can really project ourselves into long-term challenges, like building infrastructure that solves hard problems, not only incrementally improving on the state of the art. And this is really what I like to do. And at the same time, we have accesses to absolutely immense resources, both computing platforms, next generation algorithms, models, clients that internally and also on the cloud want to use our systems. So it's a unique opportunity. And maybe most important is the people there. I mean, the researchers, but also engineers and people who make all of this happen, translating research to products, building super great systems, many of them being open source and contributed to the community. There are very few places in the world like Google for that. So I will not generalize to arbitrary labs where many other companies do great engineering, but I feel particularly privileged to do this at Google because of that. So what's next? It's a very broad question. From my standpoint, because of course I only know so much, and I don't want to speak of things I don't know anything about, I would say that there are very big challenges ahead. One of them is, I mentioned the performance, like scale of the models that we are running, we are accelerating, running on many machines, many parallel machines. So this involves immense engineering skills and also computing resources. So breaking these computations down to something that's more tractable, that's something that maybe consumes a lot of data, but doesn't at least require so much engineering expertise to make it run, is definitely a huge challenge to go forward. So you heard about ChatGPT. The way these models will scale in the future is even more frightening. We are talking about terabytes of data in the models, so which is not something that you would run on your phone today or in the near future. So we need to really address those scalability problems, and Google, of course, in research is working on that. Lots of people are working on that. Another thing that's very close to my heart is safety and understanding how these systems interact with physical systems or with humans or like the rest of the physical world. And I think ML so far has been super successful at doing things that eliminate the need for a lot of human intervention in what we could call like feature engineering, or kind of thinking a lot about the problem beforehand, and instead automating the process of discovering all these like correlations and causality links, etc., automatically. But I think we need to go way beyond that. We need to make sure that it also interacts safely with control systems. For example, in automated driving, you see all these fancy systems coming up, but it's very difficult today to have any assurances of their safety, and what are the scenarios where they will fail, how they will fail, how can we get assurances, like even maybe using, again, formal proofs of correctness. What does it even mean to prove the correctness of a self-driving system with AI inside? These are completely open challenges. So this is maybe not, for example, Google Research may not be the most advanced place for research in these safety-related areas, but I think in academia there is a lot of work happening there. So to me, these are the biggest challenges: scale and safety. Okay, that's a great question. So my talk yesterday was a bit more focused, of course, for a technical audience. But one of the challenges I'm focusing on in my research is, as usual in computer science, we try to automate some of the process that we are doing manually, to the point that we are putting ourselves out of a job even. And in that sense, a great challenge for artificial intelligence is to automate the construction of compilers, is to automate all the intelligence we put into building systems that do these fancy optimizations, like translating from human language down to the machine. So you know that these translations from like human languages to another human language, like Chinese to English, work pretty well these days. I mean, at least they are making huge progresses. It's not quite the case for computer languages, programming languages. Of course, these systems are very different. They are formal semantics. If you make like the slight mistake, it will probably do nothing at all or not what you expect. So it's related with the safety problem I mentioned, by the way. How do you make sure that AI systems get super accurate or have guarantees of operation and correctness? So automating some of these compiler processes of translating languages is a big part of what I try to do. And in the lecture, I was mentioning retiring libraries as one of the challenges, being that right now performance is mostly, although I mentioned compilers are as tools capable of parallelizing your like human readable programs into things that run faster than the machine. In fact, most of the performance today is obtained through what we call library routines, like being written by human experts who are like the ninja programmers of CPUs and GPUs. And most of the ML machine learning frameworks actually orchestrate those library routines to get good performance. So we need to also automate that part. And that also that also involves a lot of artificial intelligence to capture what's the expertise in writing these efficient programs. So once again, I'm not the specialist of this. You may want to interview a computer architect who's live, depend on answering that question. But definitely, yes. The main reason is physics. I mean, if you want to get low power, energy efficient devices, these days there is no alternative to specialization. I mean, we have of course explored a lot of technology like circuits improvements to reduce power consumption, and the progress in that field is incomparable with anything else in the rest of the industry. But still, we are reaching the limits, and right now specialization, task specialization of the hardware is absolutely key. So whether it will specialize for every subfield or type of architectures in like model architectures in ML. Probably not, because first of all, I think there are more like patterns rather than like individual models that require an individual accelerator. So, and there are not so many different patterns. So, for example, today it's all about transformers. A few years before, it was all about convolutional neural networks. So, these are like similar patterns but different that may require different accelerators. So, GPUs you mentioned, graphical processing units that are not limited to graphics at all. They are very good for both convolutions and transformers, but you could imagine even more specialized architectures for one or the other. But I don't see like a flurry of devices for ML to grow beyond a few patterns, which maybe there would be dozens, but not. That's already a lot, not much more than that. But now in other fields, yes, of course. Like if you have enough money, basically, you can have a chip for your own purpose. If you have an ecosystem around it, typically in mobile or edge computing devices like smart appliances at home, etc. You want to do signal processing coupled with machine learning to detect I don't know, like intrusions in your house, or to optimize the heating, etc. These may eventually require low power devices that are very specialized to the task, and perfectly good reasons to have specialized devices in that field. Yes. So I can tell my story. I don't know if it generalizes, but in many cases, at least in my generation, you would see people who are more, let's say, math inclined go towards computer science because it's fun, because it's so much natural, because we have been born with computers, and of course the newer generations it's even more the case. But maybe my generation was particularly the case because the machines we were dealing with were getting very powerful already. Even they already had accelerators, hardware accelerators at the time, if you know about the Amiga, for example. And at the same time, they were very low level in terms of the programming interfaces. So there was not like all these stack of Python and amazing things that do everything. It's given to you. No, you had to do everything. I mean, the basic software environment was very poor, and already much better than what was there like 20 years before. But and so I had no choice but go into computer science education because I liked math, but I really liked computing even much more, and I could do a little bit of math in that field, so that was natural direction. And then I think I always wanted to do research. I was curious. I also, maybe that's natural from in my family. There are lots of researchers, so that was natural to do that. But I wanted to do research in connection with engineers, like building real systems from the start. I got a compiler course in my first year of master's that was super well taught and exciting, and we got an assignment, a project that really got me interested in compilers more specifically. But even before that, I was curious about programming languages, and so I decided to go for a PhD in that field, in compiler construction and parallel computers and the like. And then I went for an academic career because that was there was a door, it was open, I got in. No, it's a little bit more complex than that, but I got lucky enough to work with great colleagues, great advisor and co-advisor, and got some visibility for my research, although it was still very theory oriented. So it's only after I did a postdoc at the University of Illinois that I really started working with more practitioners, for example, computer architects, caring about performance for real machines, not just theory problems, and started to collaborate with more people in that side of the world, building actual parallel systems, not just trying to solve parallelization problems in theory. And step by step, I started building platforms because this is what I like with students, contributing tools that became part of open source platforms in operating systems and compilers, and eventually willing to go beyond. And as I said, joining industry for doing that. So I recently, partly because of COVID, I decided to move away from Paris. And so I'm still actually commuting between the Paris lab and home, where I also work. So I also enjoy mountaineering mostly, winter and summer. So I'm in the Northern Alps, which is not the worst place to be. Although, of course, Scotland also has a lot of amazing mountains, and even I know you can even ski these days. So I do a lot of skiing and mountaineering, and I guess that's enough for now.